and gas compressors generally when we are dealing with gas power plants. Similarly, pumps. Of course, pumps we don't have in the syllabus of GATE, but in vapor power cycles we go for steam turbines and also gas turbines. Okay, this is for ESE, and here also we have ESE actually. Clear? So these two books are a very good set for ESE, but for GATE level problems and all, 𝐂𝐿 is good enough for nice problems and all. So once you start understanding the concepts and also you start seeing the devices, then you should start putting in math into it. Okay, but if you use condenser, that happens at low temperature, and this TLM actually decreases because of condenser. Hello all, कैसे आप सभी लोग? So इस वीडियो में हम important topics of applied thermodynamics discuss करेंगे. So you all know in basic thermodynamics we see laws normally, okay, like first law, second law, all these things, okay, and we do certain mathematical stuff so that we could understand some equations. लेकिन applied thermodynamics में we'll apply these laws to some devices. Like मान लो कि आपके साथ एक पंप है, so इस पंप को first law of thermodynamics कैसे apply करना पड़ेगा. So we'll learn all these things in applied thermodynamics. Okay, so in this video I'm going to list about some few important topics from where questions could come. Actually, this analysis was completely based on previous year papers. Okay, now let's see. If you first reveal, this is one of the very important subject actually in industries. The reason is, in industry, let's suppose when I was working with HPCL, this is a HPCL refinery picture. Actually, you can see in the night shade, you can see a lot of devices and all. Okay, and normally if you go to refineries and work there, it's not like people ask you to write first law of thermodynamics, what is second law of thermodynamics. You have to apply that to devices like pumps, heat exchangers, compressors, turbines. There are a lot of devices which actually exist, and you should know how to apply your energy analysis to your devices, okay, for controlling the flow rates and all the things. So anyway, if you come to GATE examination, coming to the GATE syllabus, so this is the syllabus for GATE mechanical as well as GATE XE. The syllabus of GATE, the syllabus of applied thermodynamics is slightly less for XE as compared to mechanical. Okay, so in mechanical, so if you go step by step, so in mechanical we have power engineering. So basically we'll talk about power plants and all a lot in this applied thermodynamics. So we generally focus on gas and vapor power cycles. Okay, so vapor power cycles and gas power cycles. So in a power cycle, we generally have a compressor if it's a gas cycle, and you have a pump generally if it's a vapor cycle, like generally the liquid vapor phase transition happens. So these things are actually present, and these are just the devices, air compressors and gas compressors generally when we are dealing with gas power plants. Similarly, pumps. Of course, pumps we don't have in the syllabus of GATE, but in vapor power cycles we go for steam turbines and also gas turbines. Okay, and concepts of regeneration and reheat are very, very important, especially for mechanical exam. Okay, because in XE you can observe carefully, along with Rankine cycle we have only Rankine reheat cycle. Okay, generally regeneration concept is not there in XE, and right till now there is no question of regeneration in GATE XE. Okay, but in mechanical majority times questions comes from reheating actually more than regeneration. Okay, or sometimes they ask you 1 mark questions where they ask you about the effectiveness of regenerators, all this simple basic stuff. Okay, then if you talk about IC engines, we have 3 cycles: auto, diesel and dual cycles, but whereas here also we have only auto and also diesel cycles. Okay, and generally we don't get many of the questions from dual cycles. Generally the focus is on auto and diesel. And coming to the last module, refrigeration and air conditioning, vapor and gas refrigeration systems. Comparatively, vapor has higher weightage as compared to gas refrigeration, because gas refrigeration cycles are generally somehow covered in case of this gas power cycles in general. And properties of moist air and basic psychometric process, which here also you have a little bit. Okay, of course it's not mentioned directly here, but when we are dealing mixtures of gas, they will talk about properties of moist air, because moist air can be treated as dry air plus water vapor. So anyway, if you go step by step analysis, here I have divided the syllabus into 3 modules. One is power engineering, one is IC engines, and the last one is refrigeration and air conditioning. So if you go step by step, in IC engine cycles, we have seen these are the 3 topics which you have in IC engines: air standard, auto and diesel and dual cycles. This is the order of preference. Like normally questions come very often from these 2, auto and diesel as well. So these are highly probable topics, which I have marked in green, are highly probable topics, and this is a standard dual cycle. I'm telling you this references or this weightage I'm giving you only for GATE examination. If you go for ESE, the syllabus is vast for ESE. In applications of thermodynamics, we have detailing of so many devices, individual devices, but this is as per the GATE reference. And for references, you can always follow this fantastic book, Thermodynamics and Engineering Approach by 𝐂𝐚𝐿, and also Basic and Applied Thermodynamics by V. Ganeshan sir. His book is very famous for IC engines as well. So recently, 4 or 5 years back, he has launched a book on Basic and Applied Thermodynamics, which have some very good questions on IC engines and in general basic thermodynamics also. Okay, so you can go for this. So anyway, please focus on these two things in a broad sense. Then coming to the power engineering, so vapor power cycles and gas power cycles, basically your Rankine cycle. In this case, we'll talk about your Rankine cycle, and also in this we majoritarily focus on Breton cycle and its reheating and regeneration concepts accordingly. So these are the two things which many of the times questions come. Generally it quite happens that if one year they ask from here, the other year they shift to gas power cycles. It does happen generally, but it's not guaranteed. Again, you know, I'm just telling you the analysis, not astrology, so I'm not predicting what's going to come in the future, but what generally happens is what I'm telling you. Okay, so this is what. And air and gas compressors, and of course when you're dealing these two, you know, in Breton cycle we deal with compressor and gas turbine. In case of vapor cycles we deal with pumps and, you know, steam turbines. So basically we have to have certain idea on compressors and turbines. That's it. So a bit of mathematical stuff, but again the questions from this are very you know, less in general. Even if some question comes, you can solve it with the help of basic thermodynamics concepts, basically applying your steady flow energy equations and all. Okay, so that's why this is very simple. Now for gate you can go with thermodynamics and 𝐂𝐚𝐴. Normally this is for gate, which is good enough. And 𝐂𝐤𝐴𝐐 plus I'd like to also add one more book, 𝐂𝐚𝐭𝐜𝐡, which is very nice book for power plant engineering. Normally this is power plant engineering, and these two books, basic and applied thermodynamics by 𝐂𝐤𝐴𝐐 and this you know, power plant engineering by 𝐂𝐚𝐭𝐜𝐡. These two books are a very good set for ESC. Actually this is for ESC, and here also we have ESE actually. Clear? So these two books are a very good set for ESE, but for gate level problems and all, 𝐶ENGEL is good enough for, you know, nice problems and all. And the last part, refrigeration and air conditioning, we go for VCRS. Normally VCRS is one of the most frequently coming topics of refrigeration, and normally the gas refrigeration systems are not much asked compared to like the Joule cycle or basically, you know, some other gas refrigeration cycles. They don't talk much about these gas refrigeration cycles, but VCRS is one predominant topic. And properties of moist air, basically calculations of your specific humidity, then relative humidity, all these things they'll generally ask you. Dew point temperatures, let me write that as well. So calculation of this dew point temperatures, all these things they generally ask you to calculate for different properties of moist air. They'll give you the saturated pressures and all the basic things. Then one thing is again psychometry, basically some basic process we deal with moist air like sensible heating or humidification, dehumidification. Again all these things are pretty much easily understandable if you go through the references. Okay, and so these are the areas where topics generally come in a high sense, but this area is generally not a very, you know, frequently. I think last 7-8 years there is no question from this topic, gas refrigeration systems. Okay, so again coming to the books, for gate level this is good enough, and for ESC this CP refrigeration and air conditioning by CP is one extraordinary book for refrigeration and air conditioning. Okay, to talk about refrigerators and air conditioners as well. Okay, so on an average this subject holds weightage of 3 to 4 marks in general. So in this 3 to 4 marks, sometimes you have one mark question, 1 2 marks question, or sometimes there are instances where it went up to 5 marks also, but that's not very often. Normally basic thermo plus applied thermodynamics will combinedly give you something around 9 to 10 marks, out of which 3 to 4 marks are carried by this you know, applied thermodynamics. Okay, and this weightage is excluding turbo machines. Okay, so turbo machines in sense your hydraulic machines. Okay, so in hydraulic machines generally you will have 1 to 2 marks, sometimes 1 mark question comes out, or sometimes 1 2 marks question comes out. So generally 2 to 3 marks also comes from hydraulic machines. So therefore this applied thermodynamics holds you very nice percentage of 2 to 3 marks. Okay, and one important thing I want to tell you, the kind of questions comes in this gate examination for this applied thermodynamics is almost like saturated. Like I'll tell you, if you start solving PYQs, you keep on seeing the same kind of questions again and again. Okay, majorly on reheating of Breton's, regeneration of Breton cycles, similarly vapor power cycles, all these things. So this is again one scoring subject. These 2 to 3 marks in which this subject actually gives you is very easy to get. Okay, the only thing is slightly you should know basic bit of concepts. It's a very easy subject, but the condition is you should know basic thermodynamics in a nice way. You should understand the things in a good way actually. Okay, and for how to study this, I would like to give you some suggestion based on my experience, because I was working with HPCL and also BRC later. So if you see, first of all, in anything, first you should know the theory, what happens in a particular device. You should know how to do the things theoretically. Then you should start visualizing the things. Okay, and generally the problem with ATD, applied thermodynamics, is the kind of devices we use in applied thermodynamics, like for example turbines, compressors, or heat exchangers. In all these cases you don't see them directly in day-to-day life. Like for example, if you're last time when I was doing fluid mechanics, I have shown you if water is coming out of a tap, why the diameter is decreasing. So all these things you can analyze. But unfortunately, in applications of thermodynamics, many devices you won't be able to see in day-to-day life. Maybe few, like pumps. That's it. Okay, so if you want to have certain practical knowledge, possibly better to visualize the things, go for an internship, like in the industries what I have shown you before also. So just go for certain internship, it could benefit you in terms of understanding. Okay, because when I'm teaching power plant, I just put a box and write it's a boiler and connect it to a turbine. Okay, then I will draw the shape of the turbine like this. But if you go to industry, boiler is not just a box, it creates thousands of problems, leakages, metallurgical failures. There are a lot of things that happen. Similarly, if you go for turbine is not like this box in general. Normally we show it expansion because the turbine blades keep on expanding as you pass. Okay, so that's why we generally keep it as a diverging device. But actually, if you open the turbine, there will be a lot of blades and all. I myself have worked with GTGs, gas turbine generators, in when I was with Hindustan Petroleum Corporation. So better once have an industrial visit at least to get idea on different things. Okay, and I'm telling you, after seeing the actual boiler, looking at the problems of the boiler, it's very easy for you to write boiler as a box and talk all the thermodynamics about it. Okay, because in class and in books you study thermal engineering, but if you go to industries, you actually see thermal engineering. Okay, because heat normally, how many of you, I don't know because it's not live, so very few of you might have seen a heat exchanger, but actually if you see a heat exchanger, I'll show you, there'll be a lot of tubes inside. Okay, I'll just show you this heat exchanger if possible, which you have heat exchanger images. So normally this is how you have heat exchangers. Okay, we'll remove this word design. Okay, yep, so search. So I'll show you some heat exchangers. Yeah, this is practically a heat exchanger. You can see there'll be a lot of tubes which are inside. Actually, you can maybe see in an enlarged view. So all these are tubes and fluid flows in that tubes. Okay, so normally you see when you study, there are a lot of factors like fouling which happens on the tubes of heat exchanger. So there are plenty of things. Okay, so once you start understanding the concepts and also you start seeing the devices, then you should start putting in math into it. Okay, like basically, you know, math is like one of the tool for understanding any physical phenomena. So once you, let us suppose for example, if fluid is flowing in, then it's getting heated and coming out of a condenser tube, liquid water if you're sending, then how much heat, what should be the outlet temperature of the condenser outlet. So all these things are obtained by simple mathematical equations. Okay, so once at your level if you do these three things, then you will be in a stage to solve all the previous year questions. So once you solve previous year questions, you will get an idea to what level the questions are coming and to which level you should study the concepts to answer these questions. Okay, so once you are thorough with all these things, you can practice new questions, which is basically unsolved questions of any of the references I have given you. Like for example, here I have given you certain references like power engineering, refrigeration and air conditioning, again IC engines. So from all these books you can actually go for, you know, certain new questions which could increase your practice basically. Okay, and to avoid mistakes in exam, better solve PYQs at least twice before solving this new questions. Okay, that could give you much confidence. So that's basically from my side actually. And till the last of this video, in every video generally I share certain knowledge. So in this video I'll be answering these two questions. Why is these two are actually very famous interview questions in applications of thermodynamics. Why is condenser mandatory in a power plant? The reason why they ask you this question is, normally in a power plant, in a vapor power plant, you can see you generally have a pump, and this pump take water from a condenser, correct? Condenser. And normally if you see these condensers operate at a pressures less than atmospheric pressures, normally around 30 kilopascals, 40 kilopascals, that will be the typical ordering range. And from this pump, the feed goes on to the boiler. See, I am simply putting a boiler as a box, but actually if you go to industry, it's I myself have made certain night outs to get repaired these boilers in my shift. Fine. So let's have a turbine as well. Okay, so this is your turbine, for example. Now if this is your turbine, then clearly you can understand whatever comes out from the turbine will go into the pump via this condenser. Okay, now in interviews people ask you, let's suppose if I delete this condenser and if I connect a reservoir. Okay, so this is a fresh water reservoir. Let's suppose some large amount of water is already available to you. So this is a fresh water reservoir actually. Okay, so if this is a freshwater reservoir, then directly I can leave the turbine exit into the lake or river, whatever, and you can take pump inlet from the same lake or the water body actually. But this can be done. Power plant will operate even in this condition without the condenser, but one problem is your efficiency will fall drastically. Okay, the reason is, see, Normally if you draw TS for this, I'm just drawing a rough sketch. TS, if this is the vapor dome. So initially whenever the fluid is in pump, it's in liquid phase. Then after it gets into the boiler at constant pressure, some heat addition happens. Then in the turbine it expands well, and in the condenser there is a heat rejection. Okay, so this is a condenser. 1, 2, 3, 4. This is a small cycle, Rankine cycle I'm drawing. Now if you understand one thing carefully, this last part, okay, if you don't have this, normally the thermal efficiency of the cycles is 1 minus TLM by THM, where these are mean temperature of heat additions. Normally what happens in case of Carnot cycles and all, when you do second law analysis, you will get the formula 1 minus temperature of heat rejection by temperature of heat addition, because heat addition and heat rejection happens at a fixed temperature. But in cycles where you don't have a constant temperature heat addition or heat rejection process, we define some quantity called the mean temperature of heat addition, and this mean temperature of heat addition decides. Now when you have the condenser, since heating is done in this phase, means from 2 to 3 it's heating, so we define some mean temperature of heat addition. Now if you have a condenser or a water body, this THM doesn't change, because THM is related about this. But if you are not using a condenser, then try to understand, here the condenser phase change happens, okay, and you know temperature of phase change is directly proportional to pressure, and here we are actually changing the phase at a low pressure, correct? So than the atmosphere. If you are doing a phase change at a low pressure, that means the temperature of the condenser is also low as compared to the normal atmospheric phase change temperature. Normally atmospheric conditions, phase change happens at 100 degrees Celsius, but if you use condenser, that happens at low temperature, and this TLM actually decreases because of condenser. Okay, so this decreases because of condenser, and clearly if this decreases, your thermal efficiency will increase. Okay, if you don't have a condenser, the phase change, or basically this water will be at normal conditions, atmospheric conditions, and that will actually, the temperature of heat rejection will actually increase. Okay, because hot outlet from the turbine is the heat rejection temperature, and this line which is here will actually get lifted up, because phase change will happen at a pressure which is equal to atmospheric pressure, which is greater than this PC. Okay, clear? So that's why the thermal efficiency will increase, because of this presence of condenser. Plant can operate even without condenser, but efficiencies will fall, which you don't want to happen. And this question, why is heat addition in Otto cycle a constant volume process? The problem with basically the advantage of this constant volume process is, look, I'll tell you, if you have an engine, generally Otto cycle is designed basically on the basis of spark ignition engines, correct? And the substance that we use is gasoline normally. Now the problem with this gasoline is knocking. Okay, you cannot compress this too much because of knocking. Knocking is what, basically whenever you are trying to compress the fuel air mixture practically, okay, so because of the compression of fuel air mixture, small pockets of fuel get accumulated at one location, and they start igniting before the piston reaches the top dead center, which is actually not very good for the combustion efficiencies. So this knocking, now to avoid this knocking, what we should do, we'll actually compress due to this limit on, there is a limit on compression ratio, because if your compression ratio is limited, then definitely the pressure to which you actually compress also limit. Okay, and to avoid this, normally to avoid this knocking problem, nowadays we got this sparking fuel injectors and all, fuel injection systems and all, but when this cycles, Otto cycle, diesel cycle were developed, the main intention was this. Okay, now knocking is the problem. Now when there is knocking, you definitely have a limitation on the compression ratio, you cannot go beyond such limits. Okay, so therefore we use spark plug. So we use a spark plug actually, okay, which you generally see in bikes. Outside it's visible. Normally sometimes you open it and clean it if engine don't start soon. So we use spark plug. Now when spark plug is used, what happens is, by the time the piston comes, let's suppose if this is your top dead center and you have a small spark plug here. So if you have a small spark plug, then what happens is, the air fuel mixture will be at very high pressure here comparatively. Then whenever, as soon as you give a spark, what happens, since you are physically giving some external heat source, the blast happens all of a sudden, and the blast speed is so high such that within that time the movement of the piston is very small. Reason, whenever the piston is trying to reach top dead center or bottom dead center, the velocity of the piston is very slow, correct? because what happens, the piston actually travels, reaches TDC, then again reverses its motion. Okay, when the piston is reversing its motion at a particular point, near to that point the velocity should become very close to 0. Yes or no? Let us suppose if my function is causing from negative to positive, then in this domain, in this region, the value of the function will be very less. So that's why the velocity of the piston when it reaches top dead center is actually very small. So within that small time, within the small movement of the piston, complete combustion happens. So the heat addition happens all of a sudden. So that's why within the time of heat addition, the piston physically cannot move a great distance. So that we'll assume the piston is not moving and it's staying there to easier analysis. That's it. Okay. So that's why the heat addition is basically a constant volume process. That's it. Okay. Since you are till the last part of this video, I thought of giving you 2 questions. But anyway, the main agenda of this video is to tell you what are the important topics that can come in GATE examination from IC engines, these 2, and from power engineering cycles, vapor and gas power cycles. With these concepts in XC, you don't have this regeneration concepts. Okay, you may have reheating concepts but not this regeneration concepts. And in refrigeration and air conditioning, these are the 3. Majority of the times questions come from 1 mark for this topic. Okay, normally 1 mark questions are very often, you can see, from these properties of moist air. Okay, so that's how we have different things basically, and this is what I told you how to study basically here. So since in applied thermodynamics majority of the devices are not commonly seen outside, so better if possible you should go for an internship to understand the things much better. Okay, but for GATE examination, just knowledge a bit of books is important for you to excel in the exam. Okay, so then yeah, these are the 2 questions which I thought of answering, and yeah, so thank you, that's it from my side. Okay, so I hope if you have any doubts you can type in the comment box of this video. I'd be available to answer you. Okay, and also if you want to reach me out, this is my Telegram ID, t.me/pwvinay. okay, so this is my Telegram ID actually, so you can actually join there if you wish to join, if you feel that I can help you out somewhere. Okay, yeah, so that's it from my side. Then wish you all a very good luck for your GATE 2024, and from 18th of this month I'm going to start fast track mechanical course on your YouTube channel, GATE Wallah Mechanical, for this applied thermodynamics. Okay, I'm going to take applied thermodynamics instead of Vinod sir. I'm replacing it due to certain things. So we'll start from 18th of December from 4 p.m. to 6 p.m. Okay, so we are starting fast track applied thermodynamics. Okay, I'll try to make things interesting there, much more interesting. Okay, so we'll meet then. Thank you all, take care and keep preparing. Bye.